All right, so this next example is essentially the same thing, but just with different vectors, same question. So we've got a vector b, it's a three-dimensional vector, and we want to know if it's a linear combination of these two other vectors, a1 and a2, which are both also three-dimensional vectors, okay? So how are we going to do it? We're going to start the same way. What would it look like if the answer was yes? And this is a chance to remind yourself, what is a linear combination, right? What would it mean for b to be a linear combination of a1 and a2? Well, it means you can write b in this form. It means you can multiply a1 by some scalar c1 and then multiply a2 by some scalar c2 and then add the scalar multiples together and see if it's possible to do that in such a way that you get exactly b. So start by just writing it down and then follow your nose. So the next line, you just rewrite this but with the actual definitions of a1, a2, and b. So we get 3 negative 4, 1 is equal to c1 times a1, which is 403, plus c2 a2, which is 1, 2, negative 2. Okay, and remember the previous observation that we just made. This is equivalent to the linear system that has an augmented matrix given as follows. The coefficient matrix is just going to have a1 and a2 as its column. So its first column is going to be a1, its second column is going to be a2, and then the constant column is going to be the vector b. Okay, so that gives us this augmented matrix. And just let me take a moment to reiterate what I said before. This is a bit of a jump, right? Doing this in one step is we're really taking advantage of the observation we made. If you're ever uncertain though, you can always follow these steps. In fact, I'd encourage you, maybe even want to pause the video right now and fill in the details yourself, just to go through this process again and show that you really do, or I guess I could have circled this as well. This is the full story, right? In the previous example, this is where we showed all the steps. I essentially skipped over all of these steps. So you may want to work through those just to remind yourself what's going on. But in any event, you're going to end up getting this linear system, and if you want to know if it has a solution. So let's solve it. So let's take row 2 and multiply it by half. And what will that give us? First and third rows won't change. And then we'll just have 0, 1, and negative 2. Okay, so I'm seeing that column 2 is going to be a pivot column here. And then I'm going to use this 1 to clear out the entry above it and below it. Okay, so I'll take row 1 and replace it with row 1 minus row 2. And I'll replace row 3 with row 3 plus 2 row 2. Okay, and that's going to get me the following. We'll have 4, 0, 5. 0, 1, negative 2, that row doesn't change, and then the third row is going to become 3, 0, 7. Okay, and then, no, something seems, yeah, I did it again. This shouldn't be 7. What was I doing? How did I get 7? Anyways, that should be negative 3. Okay, I think I was adding the 3 twice instead of the negative 2. Okay, so anyways, and now I'm going to take row 3 and replace it with 1/3 row 3, and that's going to give me this. This will give me 4, 0, 5, 0, 1, negative 2, 1, 0, negative 1. I'm not following the Gauss-Jordan elimination method exactly because that would form fractions. That would introduce fractions, so I'm trying to avoid fractions. Now I'm going to interchange rows 1 and row 3, and that's going to give us 1, 0, negative 1, 0, 1, negative 2, 4, 0, 5. And it looks like this is not going to work, but let's just carry it through all the way to the end. So I'm going to take row 3 and replace it with row 3 minus 4 row 1. And what's that going to give us? So row 3 is going to turn into, we'll have a 0 here, a 0 here, and then a 9 here. And now you see there's one of those contradictory rows, right? Because this is equivalent to the equation 0c1 plus 0c2 is equal to 9. So I'm just going to write contradiction. So that means there's no solution. Therefore, this is impossible. It's impossible to make this equation work, and therefore the answer is no. B is not a linear combination of A1 and A2. So I'm going to say, therefore, that's what these 3 dots, did I use it in the last example? I did. I guess I didn't make a comment. These 3 dots, that just means therefore. It basically means you're about to make a claim which is justified by the work that you just did. So you're essentially going to write a conclusion that follows from the work that you've done. So we can say, therefore, B is not a linear combination of A1 and A2. So that is that example.